now we know this, the notations of the system dynamics, and let's see some design patterns of these system dynamics models. One pattern is reinforcing the pattern. So reinforcing loop through the flows. So it has, okay, so here we have one strange notations here. This is an outside source. Usually it is being treated as a stock with infinite amount. Okay, so this is a stock that can forever flow from this outside source to the internal stock system, okay, within our system. However, of course, that flow is being regulated by this flow model. Here, we have a balance. Let's put this thing into our context. This is a banking account balance, let's say. Okay, banking account balance. Let's say we put 100 here, our balance, and let's say the interest rate is, let's say, 5%. This is being specified what? Parameter and specified initially. And then this parameter and the stock is being utilized to make the flow specification, and the flow is being modeled, interest rate flow is being modeled, balance, multiplication of interest rate to rate. Okay? So meaning that from the outside, 105 is being modeled and flow, let's say 5. However, that is being added to this stock. In the next time step, then it will be 105. And 105 will be computed. And what it says is that from 5 flow to this, it's going to be a 5.25 flow increased. And later more increased, and so forth. Eventually that will be turned into like this. We only had multiplications in our specification model. However, from the flow model, we are going to specify the adding up part to this stock. And this loop, positive loop, reinforcing loop part is being modeled through the link, stock to flow link, and the parameter to flow link. Okay? Even though there is no quadratic specifications in this system, the result is being quadratic. Because that we are modeling here how this balance is being modeled, because it is being specified by dt over dx, dx over dt. Okay? And dx over dt is being modeled by a single flow, and that part is being modeled here, and this will be brought into here. Even though this is a first degree, okay, first degree polynomial. If it comes to dx over dt, then it will make a second degree polynomial. Then it will make these types of results. Will work like the quadratic system. So this is a reinforcing loop. Let's discuss a second system dynamics design pattern, which is being called saturations. Okay? So this is a typical plateau reaching behavior. We have this fluctuating system, and let's say this is a control level. We want to make this control level meet. However, our current value is being here, so that it should be approaching like this. If it is being nicely behaving, Then how to model this changing behavior? That's the questions. So system wants to reach a certain goal, and by reducing the discrepancy between the state of the system, this is the state of the system, and the system goal, control level, or being aka system goal. And we want to calculate the discrepancy, this level. This is being discrepancy, right? So by injecting this discrepancy level over time, we can approach to this control goal. Then how it is being modeled. From the outside source, we are going to add up to the stock state of the system, how the first approach rate, how fastly, how quickly it is going to approach. Let's say is 5%. And the system goal is being set. Let's say currently, let's say system level is like 50 and system goal is being 100. And the discrepancy is what? 100 minus 50. And the approach rate is that 50 multiplied 0.05 is how much? Is like 2.5, right? Then we add up to this state of system plus 2.5, so make it 2.5. So a little bit closer. However, next time step, we have 2.5, 2.5, meaning that discrepancy will be reduced, and this flow will be reduced. However, still adding up. It's going to be increased close to the system goal. However, the increment level is being a little bit reduced. Okay? So that this is initially, at the initial time, the increment is big. However, later, the increment is being small if we compare these two. So, because of that, it is showing the saturation behavior, because as time goes by, we are going to nicely be getting closer to the system goal, but this level of this discrepancy will remain. Okay? However, what it says is that it is giving the stock this amount of the approached flow right away. But that is not being realistic. In the real world, from the outside source to the within our system stock, it takes time to flow. So if we add that delay, how the system will turn into? That's our next question. Right, this is our final design pattern for the system dynamics, which is being called oscillation. This is exactly the same structure like the previous saturation case, because that we have outside source, state of the system, and the approach rate, and system goal, and discrepancy is being multiplied to the approach goal and flow. However, one thing difference is that we have a delayed response from the system. When there is a delay, the discrepancy amount is not being added up to the stock right away. Then it becomes a problem. We already observed this, reasoned about this type of problem where the oscillation case with the causal loop diagram. Okay? And what you can see here is these oscillations, like the bullwhip effect. However, it is not always the bullwhip effect. Sometimes it approaches the control level like this. Okay? So that eventually it will converge. It is not saturating, but it will converge to a certain system goal. However, in a certain case, our approach will make the bigger oscillations, like this. And this will make a bullwhip effect. Rather than this convergence. And what's the difference between these two cases? That is actually this approach rate. These two systems will still work with the discrepancy-based correction. However, if approach rate becomes different, then this overshooting behavior becomes worse. Overshooting means that rather than convergence, it overshoots. So this is the overshooting. And this overshooting behavior, if it becomes large, then this oscillation will be impacted. So approach rate will make one factor of that problem, oscillation case. Can you find another factor in this oscillation case? That is being what? That is being how much being delayed. If the delay is very short, then it will work like just a convergence, the saturation case, if the delay is very short. However, if it becomes too much being delayed, this oscillation, even though approach rate is small, it will impact. Okay, so this delay factor and approach rate factor, basically these are two factors. These two factors are controlling the convergence speed, and these two factors will determine whether it will converge or turn into a big oscillation of the bullwhip effect. So these are the three basic patterns of the system dynamics, and I hope to see you in the classroom that we are going to explore more system dynamics on your own topic.